Okay, hello everyone, it's Salar and we are in part 42 of our tutorial, a tutorial to writing a real-time operating system like before. In previous part, I talked about circular list and circular queue. Circular list, as I said, circular list has its implementation in C, but circular queue like queue implemented by a list, in this time by circular list, okay? But in this time I want to talk about a new type of data structures, tree. I want to talk about tree or binary tree. As I said, list is a linear data, a linear data structure. Okay, but a tree is not a linear data structure or binary tree. Binary tree is a data structure but is not arranged linear. It's look like three branches. For example, assume that you have a upside down three branches like here. Okay, here is tree. Okay, but as I said, a list is arranged in a linear form. Okay, one by one, sequentially arranged linear. Okay, and a tree or binary tree is a sorted data structure and sorted by key nodes. Okay, by key node. Okay, for example, assume you have a list that its keys, for example, is 1 5 2 0. Assume that here is your key. This list is not sorted by its key. Okay, but binary tree is sorted by keys, and I will say you in next slide how a binary tree is sorted by key. Okay, but assume here is a binary tree, here is nodes, and here is key of nodes. Okay, it's like three branches, and it's not a linear data structure. But let's see binary tree properties. First, a binary tree has one root node, okay? Here is roots. In up of the tree, on up of a tree, okay? And each node has one parent node and two children, left child and right child. Each node has a parent. For example, parent of 3 is 4, parent of 6 is 4, or parent of 7 is 6, or parent of 2 is 1. Okay, but 4 has no root, has no parent. Okay, root has no parent. Parent of root is nil, and each node has a right child and left child. Left child of 4 is 3, and right child of 4 is 6. Left child of 6 is 5, and right child is 7. Right child of node 1 is 2, but this node has no left child. Left child is nil, or parent of 4 is nil node. Okay, here is root, and these nodes are leaf because they have no childs. Okay, left child and right child are nil. Okay, 2, 5, and 7 in this tree are leaf. Okay, but number 3 is so important. most important property in binary tree. Left child key is smaller than parent key, and right child key is greater than parent key in each node. Left child key, for example, for left child key 3 is smaller than 4, but right child key 6 is greater than. For 6, left smaller, right greater. For 3, left smaller, has no right, and 2 has no child. Okay, the leaf. So in each binary tree, left child key is smaller than parent key and right child key is greater than parent key. Okay, but before to talk about implementation and sequence of this data structure, let's to talk about binary tree insertion and see how we can insert a node in a binary tree. Here I have an algorithm, but let's describe this algorithm in this example. Assume that you want to create a tree by these nodes. Here is a list of key nodes. For example, assume that here is a 4 is a key node, 3 is a key node, and 6 and 1, 2, 5, 7. And in order from left to right, I want to insert these nodes in a tree. First, if your tree is empty, inserted node is root. Okay, my tree is empty, so 4 is root, and as I said, each node has 2 child, left child and right child, and parent of 4 is nil node. Okay, and another time here is nil node and nil node. Now I want to add 3. Check 3 by 4. If is smaller, go left. If is greater, go right. 3 is smaller, go left. Here. Now here is subroot. If this subroot is nil, replace it by 3. Now 3 added. Now 3 added to this tree. Now I want to insert a node with 6 in its key. 6 is greater than 4, go right. Okay, because right child key is greater than parent key. Here is subroot, and because it's null, replace it by this node added, and each of these nodes has 2 child, but in this time these childs are nil. Nil, 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 nil. Okay, now I want to insert 1. 1 is smaller than 4, go left. Now here is another time subroot. It's nil not. Another time go left because the 1 is smaller than 3. Now here is subroot, and here is not subroot. It's nil, yeah. Replace it by 1. 1 inserted. Okay, and 1 another time has 2 children, and these are nil nodes. Now I want to insert 2. Smaller than 4, go left. Smaller than 3, it's not nil, another time smaller than 3, go left. It's nil not, it's 1. It's greater than 1, go right. Here is nil, yes. Replace it here, and has 2 child. nil node. I don't draw these nodes anymore. 2 is added. 5. 4, 5. Greater than 4, go right. Smaller than 6, go left. It's nil, yes. Replace it. 4, 7. Greater than 4, go right. Greater than 6, go right. Here is 7. Now you can delete these nil nodes. Okay? Here is my 3. 4 is root, and 2, 5, 7 are leaves. Okay? So here is like this tree. So here is algorithm of binary tree insertion that I described it by this example. But as I said, a binary tree is a sorted tree. Let's see how. Because the binary tree is a sorted tree, you can find a node with maximum key in your tree. Maximum node in a tree is a node with greatest key in a tree. The most right node. If you want to write maximum, go right as much as you can. Go right. 7 has no right child, so 7 is maximum. Okay? Or for example, in this subtree, you can find maximum from root. This is the root of this subtree. Go right. I can't go right because it has no right child. So here is max of subtree. Okay? Go right as much as you can. In this way you can find maximum. Or you can find minimum node with the smallest key, the most left node. In this time, go left as much as you can. From root, go left. 1 has no left child, so here is minimum. Or for example, in this subtree, go left to 5. 5 has no left child, so here is minimum of subtree. Okay? Or in a binary tree, you can find successor of a node. But what is successor of a node? Node with smallest key that is greater than the node. So what's this description? For example, assume that you want to find successor of node 4. Here is the node. Okay, I want to find the successor of this node, the node. A node with a smallest key that is greater than node 4. Here is node 5. It's greater than node 4 but has a smallest key than 6 and 7. Okay, so how can I find a successor in a tree? If the node is non-leaf node. Okay, here is 2, 5 and 7 are leaf nodes. Okay, but 4 is not a leaf node. Minimum node in its right subtree. Right subtree of 4 is here. Minimum node here is 5, so successor of 4 is 5. Okay, but how can I find a successor for a leaf node? For example, for 2. 2 is a leaf node and I want to find the successor of node 2, node with key 2. Go up, go to the parent up. Okay, go up means go to parent and find first node that the node is in its, here is the node, in its left subtree. Go up here. If the node is in the left subtree of one node, 2 is in right subtree of node 1. So another time go up. If node 2 is in left subtree of node 3, this node, yes, 2 is in left subtree. Here is left subtree of node 3. Okay, so 3 is successor of node 2. Okay, 3 is successor of node 2. Another time do this work for node 5. Go up. Is 5 in left subtree of 6? Yes. So 6 is successor of node 5. And 7 is maximum, has no successor. Okay, because you go up to root and 7 is in right subtree. So 7 is maximum as has no successor. Okay, so your maximum, he has no successor. So here is an algorithm to find a successor for non-leaf node and a leaf node. Okay, but predecessor node with greatest key that is smaller than the node. For example, another time the node is 4, the greatest key but smaller, 3 is predecessor of node 4. For non-leaf node, maximum node of left subtree, maximum node of this subtree is 3. Or 4, for example, leaf node for 2, go up, in this time in right subtree, 2 is in right subtree of 1, so 1 is predecessor of node 2. Okay, or for example for 5, go up, it's in left subtree, another time go up, this subtree is in right subtree, so 4 is predecessor of node 5. Okay, so if you want to order your tree from smallest key to greatest key, first you can find minimum, and after that by successor go to the greatest. Successor of 1 is 2, successor of 2 is 3 until 7. Okay, so in this way you can order your node key in your tree. Okay, so a binary tree is a sorted data structure. So how we can implement this data structure? Like before, for node I have a structure, avoid the star for element. A key is so important here because the tree is sorted by using of this key. A pointer to parent, a pointer to left child, and a pointer to right child. And for tree, a data structure for tree. Another time struct binary tree, I have a size, each, as I said, each tree has a root node, and I have a nil node. As I said, the usage of this nil node is here. For example, when you have no left child, you point to nil node. When you have no parent, you have point to nil node. When you don't have parent, left child or right child, your node point to the nil node. Here nil node, 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 here nil node. But you don't draw nil node in your tree, okay? So it's not a specific and unit node in your data structure. When a node has no parent, when a node don't has parent, left child or right child, that node point to nil node. Okay, but as you can see here in repository of my project, another time in data structure include, I have binary tree. Okay, I've implemented this tree completely like Introduction to Algorithm book. Okay, if you want to see how I have implemented this data structure, read this book, Introduction to Algorithms. Okay, I've completely implemented binary tree data structure according to this book. Okay, if you are curious about implementation, you can study this book and you can find a lot of information about binary trees and its properties. Okay, so here I have a node and here is structure of the tree: element, key, parent, left child, right child, size, root, and nil. Like before, you can create a node, create your tree, insert, delete, find minimum, find maximum, search in your tree by key, find successor, and find predecessor. I write it predecessor. I should correct this function, okay, but it's not important. Here is the tree header file and here is source file. If you are curious about this implementation, you can study that book. Okay, here is implementation of binary tree in my project. So let's just see an example with this data structure in Eclipse. Okay, like before, I have an example, and if you want to use binary tree, you need to insert this header file in your code. Okay, now I want to create my tree and insert these elements by its key in tree, and I have 7 nodes, 1 to 7, and I want to create my tree and insert these nodes from 4, 3, 6, 1, 2, 5 to 7, like here, 4, 3, 6, 1, 2, 5, 7, and create this data structure. Okay, so, and after that I want to find the maximum node, maximum key in my tree, and minimum key, and after that I want to find the successor of node 4 and predecessor of node 5. Okay, so let's debug the project and see the result. Okay, first I want to run my code until here and insert all of the nodes. All of nodes are inserted. So in my tree, the size is 7 and root is 4. Okay, size is 7 and root is 4. The left child of root is 3 and right child is 6. Parent is nil. Left child is 3. Right child is 6. Okay, left child 3, right child 6. Or for example, for 6, left child is 5 and right child is 7. For 6, left child is 5 and right child is 7. Okay, right child is 7 and left child is 5. And parent of 6 is 4. Parent of 6 is 4. So here is an example about insert some node in a tree. But in this line, I want to find the maximum node in this tree from root node. Okay, from root node. In my tree from root node, the maximum is 7. But for example, from this node, maximum is 3. But from root node, maximum is 7. From root node, the node is 7. Okay, here. Or node is here. The maximum is 7. After that, I want to find minimum from root node. Okay, minimum from root node is 1. But for example, minimum from 6 is 5. But I want minimum from root is 1. Run your code. Here, key is 1 node. Here is minimum node 1 by key 1. And after that, I want to find the successor of node 4. Okay, the successor of node 4 is 5. Run the function. The successor of node 4 is 5. And I want to find predecessor of node 5. Predecessor of node 5 is 4. Successor of node 4 is 5 and predecessor of node 5 is node 4. Another time, run function. Predecessor of node 5 is node 4. Okay, in this way you can use this function and this library in your codes. Okay, so let's go back to the slides. So now you can insert some node in your tree, find maximum in a subtree, find minimum, find successor of a node, and find predecessor of a node. But here is implementation of my code. Here is some function of my tree maximum, tree minimum, successor, and predecessor. Return greatest key, smallest node that's greater than given node, successor, and predecessor. But how can I delete a node from a tree? There is 2 ways to delete a node from a tree. You can replace it by successor or replace it by predecessor. In these ways, you can preserve tree sorted. You can preserve your tree as a sorted tree. For example, assume that you have this tree and you want to delete node 4. You can replace node 4 by successor of node 4. Here, delete 5 from here and put here and replace 4 by 5. Another time my tree is sorted, or you can replace it by predecessor of 4. Delete 3 from here and put it here. Okay, in this way you can easily delete a node from your data structure and from your tree. Assume now that I want to delete node 4 from my data structure. My data structure can replace it by 5 or 3. Okay, let's just see the example. Now another time I want to insert nodes in tree to the tree, and after that delete node 4. First run my code before delete node 4. Here, as you can see, like before, the size is 7 and the root node is 4. Okay, but in this time I want to delete node 4. That's the root of my tree. That is the root of my tree. Okay, if you delete node 4, you can replace it by 5, and after that 5 is root of your tree. Okay, after that you have a tree like this. 5 is root and 3 is left child and 6 is right child, or you can replace it by 3. It's related to your implementation. Okay, so delete node 4. Now the size of tree is 6, but the root is 5. The left child of root is 3 and the right child is 6. Okay, like here, the left child is 3 and the right child is 6, and 6 has no left child anymore, and node 6 has no left child anymore, is nil node. Okay, element 0 and key 0. Here is nil node. Okay, so here was a new data structure, a sorted data structure, binary tree, and you can use this data structure when you want to have a sorted data structure. Okay, from next part I will start to implement my final real-time operating system by using of these data structures and other codes. Okay, thank you very much to see me, and see you soon in the next part. Thank you very much.